This interesting problem. Let's briefly review what we mean by composite integer. An integer is composite, providing this condition prevails. Composite really means the opposite of prime. So let's say we have divisors A and B, okay, and they're integers, strictly between 1 and the composite integer. Okay, and this just means that n is equal. In other words, also you can say n equals AB. All right, that makes it a little more. That's what we mean by composite. Okay, now we want to show there are an infinite number of composite integers which, with this condition that appears to be sort of restrictive. Now notice here I'm saying that the least prime in every composite integer is going to have a prime divisor. It's going to have, so it means it's going to have a least prime divisor. Now, but we're claiming that this least prime divisor of n is greater than the cubed root of n. Okay. Now again, that sounds fairly restricted to the point you might not expect there to be any, or maybe even a finite number. Okay, but we can actually show that there's an infinite number. But just one, I don't want to go off too much on this, but let's say that we had n is equal to 3 times 5 times 7, right? Now it's not important that that's called what, 105 when you multiply that out? But 3 is the least prime, right? So this would be the same thing as saying 3 is greater, or if n were to satisfy this condition, it would be saying that 3 is greater than the cube root. And I'll go ahead and write 105 here just so, you know. But that's clearly not true just by the form alone. But you could also rewrite this equivalently as 3 cubed is greater than 105, which where the absurdity really comes into play. Okay. So, see, neither one of these are true, right? The same statement. Okay. So you see, we just picked sort of a random integer, and it does not enjoy this property. And you got, if you try it with a few other random integers and see if the least prime integer is greater than the cubed root of the number itself, okay? Yet there is a way to show there's an infinite number, fairly easy way. Now, all I've done here is restated the problem's conditions. Let P be the least prime divisor of n. Now, of course, this is absolutely equivalent to, let me do the double arrows. This would be equivalent to P cubed is greater than P squared. I mean, P cubed is greater than, P cubed is greater than n. Is what that means. So this would have to be true in order for this integer to meet the condition of the problem. Okay, this is just a more direct way of saying it, right? But notice that this makes it, this equivalent statement makes life pretty easily if we just choose our composite number to be P squared. And a perfect square is composite, right? It has a divisor. Not, by the way, this A and B don't have to be distinct, okay? So we choose n equals to P squared. Choose n equal to P squared. And certainly P cubed is larger than our n, right? And n is a composite number. there's an infinite number of primes, so there's an infinite number of composite numbers with this property. Now this is kind of trivial. Now there's another class of numbers that you may want to figure out. It takes a little bit more time. But so since the primes are infinite, we're done. QED. Right? Due to the infinitude of the primes. The primes are infinite, right? Primes, there's an infinite number of primes. I'll just call it the primes infinitude. Okay, primes infinitude. That's supposed to be a T there, ladies and gentlemen. And I better make that possessive, right? Apostrophe, English teachers. All right, so y'all, that's it. And there's a lot more to this problem in terms of the class. There's there's another class of natural numbers that enjoy this property, and that's it. See if you can figure it out. This is sort of trivial in the sense that, you know, we picked n equal p squared, and then you get the condition being satisfied. So by an infinite number, but so far we only know that the squared primes are the only type of composite integers that satisfies these initial conditions. But there is only one more class of composites that meet it. So it's even though they're both infinite sets, the two things I'm mentioning, that's pretty restrictive. You know, it's either p squared or there's one other fairly restrictive structure of composite numbers that meet these initial conditions. See if you can figure that out. It's a fun problem. This is a modification of an Underwood Dudley number theory homework problem. I modified the instructions because I thought this was slightly more interesting, you know, or another approach to showing what he was trying to describe, this cube root of n condition and the least prime divisor. That's it, you know. But you're eliminating a lot of composite numbers from the mix here. All right. Thank you for viewing.